Okay guys, in the last video we talked about how do you get all the different colors by combining the three primary colors, red, green and blue, right? We talked about the so-called RGB color model or additive color space, and we talked about how we need three different channels inside of Photoshop and how we combine them with those three primary colors to get all the other colors. But how many possible colors we can have per image, that's decided by another element called bit depth. And that's the purpose of this video. It's a continuation of the last one. It builds up on what you learned in the previous video. So this image is what is known as 24-bit image, as we see here. Now to explain where this number comes from, I'll just pull out our old friend RGB color picker from the last video. And as you remember, we had three sliders for each primary color and each channel, red, green and blue, right? Red, green and blue. Now some of you have noticed, others may not, and some advanced users ask, well, why didn't you explain these numbers down here? Because we have these sliders and they don't go from 0 to 100%, they go from 0 to 255, and each slider works the same way. So if you count from 0 to 255, what you get is 256 different possible colors or shades of color per each channel. How do we get that number? Well, we work in what is referred to as an 8 bits per channel mode. Now we need 8 bits of data to display 256 different shades of gray, and we do that per channel, different luminance values, right? So this is 8 bits for one channel plus 8 bits for another channel and 8 bits for another channel, and that gives us this number 24. 3 times 8 gives us 24. So we're working in 8 bits per channel mode, but we have 3 channels, so 8 plus 8 plus 8 gives us 24. Now believe it or not, this image can have the potential to have, believe it or not, 16.7 million distinct color combinations. That's a lot of color, right? Doesn't mean that this image actually contains that many, but it has the potential. How do we get to this number? Well, we know that we have 256 different luminance versions of this color in this channel. We have 3 channels, right? So it's 256 for red times 256 for green times 256 for blue, and that gives us incredible 16.7 million possible color combinations. Well, if all of this doesn't make sense to you and it's confusing, don't worry. By the end of this video, you're going to have a lot better understanding of what's going on. I just wanted to give you a heads up. Now let's go really in depth and go step by step as to how we get all these numbers and why do they matter and all the other stuff. Okay, so let's start off. Now if you open up your Photoshop and if you go under your image menu and you choose mode, you get 2 sections. Now most people don't think about this, but you do get 2 sections, and those 2 sections of options really define your image. So you get to choose how many channels you want in your image, and then you choose in another section how many bits per channel, and you can choose between 8, 16 and 32 bits per channel. And this is what gives us all these different colors and all that stuff that we refer to as a full color image. Now how much you should choose, that's something we're going to discuss in the later videos, but just so you know how they work, now that's something we're going to discuss in this video, where all these numbers come from and why do they matter. So take a closer look. So when you go to image mode, you can choose between how many channels you want, and you can also choose in another section how many bits per channel, right? So for example, if you choose how many channels, well, a grayscale, that means 1 channel, so you don't even get color because you need more than 1 channel, you need more than 1 primary color, if you remember, to reproduce other colors. So what we get is essentially 1 channel, and that gives us only different gray values. This is also in photography terms known as a black and white image. Now you can also choose a standard RGB image, or RGB mode, that means we have three channels, red, green and blue. That's something we saw in the previous video. You can also try to simulate what is referred to as CMYK color space, or how you might work in terms of inks when you print your image, because when you print with 4 inks, at least standard printing does. So it's cyan, magenta, yellow, and K stands for black. You can simulate how that might look on your screen. Even though you're still displaying in RGB mode, you're actually just simulating a 4th channel. So it gives us 4 channels. Then you have a lab mode, or LAB. We're going to talk about that later. That has 3 channels. So lightness for L, A, and B. Those are like the axes you might see in Camera Raw or Lightroom. They go from green to magenta and from blue to yellow. And you have also a multi-channel. So all this information is way too much you don't need to know. Let's just focus on the first 2. Grayscale gives us 1 channel, only gray values, and for full color image we just saw we need 3 channels, RGB, red, green and blue. And those are the only 2 options that we're going to concern us in this video, as we explain later. Now, as far as how many modes, how many bits per channel you can choose, well, you can choose in Photoshop between 8, 16 and 32. 8 bits, that's a standard way of showing an image and working on. 16-bit, that gives you a lot more colors, not double the amount, but actually a lot more than that, as we're about to see. Now, you might want to use that in certain situations, but not always, and we'll discuss when would you choose that later in the videos. And as far as 32 bits per channel, well, that's a really ridiculous amount of possible colors, and for that amount we don't really need that many in a classical photographic workflow, so we might use that only when working with so-called HDR images, and that's beyond the scope of this tutorial, so we're not going to discuss that. All we're going to focus on is 8 and 16 bits per channel, and of course how many channels we have in an image. So a grayscale image working in an 8 bits per channel mode can have up to 256 possible gray values. Remember, not color, just gray values. A full color RGB image in 8 bits per channel can give you up to 16.7 million distinct color possibilities. That's a lot of colors, and we only get 2 more channels and we get this huge amount of colors additionally, right? It's pretty interesting how that works, and we'll discuss that more in the future. So what is bit depth? Well, bit depth specifies how much color possibilities can you have for each pixel in an image. Not how many you actually have, but how many you could possibly have. So that's a very important point to be made, how many possible colors you can have in each pixel in an image. Well, why does it matter? Well, if you don't have enough of bit depth, you get what we refer to as posterization and banding. And those are the things that we all have seen in our images and nobody wants. And that's the whole point behind what we just referred to as bit depth, right? That's the whole discussion about how do we avoid posterization or banding. That's the only problem we have. So let's see, what do I mean by that? Well, we're visual people, so we'll not stick to numbers for a while, right? We want visual examples. A typical problem of posterization or banding is something you might get when you're working with an image such as this one, which has a smooth gradations in the sky. And if you were to add a really high contrast adjustment, or you add vignette, well, let's try the first option. Let's add more contrast. So if I were to use, let's say, curves, and I made a really sharp S-curve adjustment which would increase contrast, take a look at the sky. We get to see this individual transitions between different tones, and these are called bands, or we refer to as banding. We have all seen this, I'm sure, and nobody likes this. So we need to understand why this happens and what all these numbers mean, so we can discuss how to avoid this in the future. You might also get to see this problem or banding when you're working with studio backgrounds, right? The same problem. We get very smooth gradations, very sharp light fall off on a smooth background, and if you're not careful when you're editing your file, you might introduce banding. Another example, there are many others, but this is one other example that I wanted to point out, is when you add an artificial gradient, right? You know, the tool for creating gradients in Photoshop, where let's say that you have a model shot against the background, you don't like the background, you extract the model, you apply the artificial gradient to the background, and then you apply some kind of an adjustment like hue, saturation, levels, curves, or something like that on top of the whole, you know, both gradient and the model. You might introduce all sorts of really nasty issues, and those are referred to as banding as well, as you can see on this example. So those are all the problems we have. We don't want to see that. So in order for us to understand why this happens, we have to take a look at how does all of this work in terms of how do we get these problems in our image in the first place. Let's go back to our familiar image we talked about in the first video in the beginning. Right, this is a full color image. Now what we're gonna be doing is we're gonna reverse engineer this image back to 1 pixel and 1 bit per that 1 pixel. So that's like the lowest common denominator, if you will. So we're gonna really break it down, go reverse engineer this image back to its origins, and then we're gonna go from that 1 pixel 1 bit back to full color image. That way you get 2 passes for the price of 1. And I think when you see that happen, you know, step by step, you'll have a much clearer understanding about bit depth and where all those numbers, you know, 256, 16 million, 24 bit, and all that numbers came from. So let's start. So this is a full color image that we all like and we work on, right? It's we don't bother much what's going on. We just know that we don't want that banding in our image or posterization. So let's break it down. Let's reverse engineer it. We know that this image consists of pixels, right, of picture elements, and we know that we have a certain amount in terms of width and a certain amount in terms of height. So for this particular image, that will be 1280 by 720 pixels. Not a very good, not a very big image, which gives us, well, just a little less than a 1 megapixel image, or just a little less than a million pixels. Well, if you were to zoom in on part of this image, you would get to see those individual pixels. And we are going to focus on just one of those. And now we're going to discuss the third dimension of this image. And it's like if you go in depth, right? That's why they call it bit depth, because it's like a third dimension. So we know in 2D that we have height and width, and many of those pixels, almost a million, create this image in terms of, you know, how many of those little tiny dots you need to create this image. We talked about how we get our color in each of those, you know, the 3 primaries, red, green, and blue. We talked about how we need 3 channels to reproduce a full color image. Well, now we're reverse engineering. Now we're going to talk about bit depth. How do we even get to our color in the first place? So let's break it down. Let's put it in essentially third dimension. Now we know that this pixel, in the layman terms, represent a minute area of illumination on your display screen. If you have many of that, you can create a really cool looking image, such as this one. So pixel, in the most simple explanation for it, would be that it's a picture element, right? You need a lot of elements in a picture to create a picture. Simple as that. Well, a bit depth, as we already discussed, specifies how much color possibilities we can have for each of those little pixels in one single image. So we know that this is a full color RGB image, and in this case we're working in 8 bits per channel mode, which gives us up to 16.7 possible distinct colors. Now if you remember, when you choose your image and your mode in Photoshop, if you remember that slide, we had to choose between how many channels and how many bits per channel. So this is 8 bits per channel, and we have 3 channels. Remember, we have red, green, and we have blue channel, and we have 8 bits per channel. Combine all that, you get 16.7 million possible colors. Well, let's strip away those channels. Let's go back into grayscale mode. So this gives us only 1 channel. So if you go back into that slide where we discuss how you can choose how many channels and then how many bits per channel, well, we just choose 8 bits per channel, and we chose 1 channel, referred to as a grayscale. Now a grayscale image is what in photography we refer to as typically a black and white image, right? But in fact it's a grayscale image. Through black and white image we only have black and only have white. This one has black and white and then has different shades of gray in between. And by the way, there are more than 50 shades of gray. More specifically, there are 256 possible gray values. That's because it's an 8-bit per channel mode. So, bit depth essentially describes what is the depth of that one pixels, how many possible shades we have per that each pixel. So it's like a third dimension, right? Now we know how we get the height, we know how do we get the width. That creates the image. We know that each of those small elements in a picture is called pixel, and now we need to discuss how do we get those pixels to show different values in different parts of an image to create what we call a photographic image, right? That's done with bit depth, and it goes from 0 to 255. So this pixel is pretty light, and it would be somewhere around here on this scale. It would be 191. That's how we would present this pixel, and the one next to it might be a different value, but it can only work from 0 to 255 as long as we work with this image in 8 bits per channel mode. What about the image in color? Well, in image in color we have the same principle, but we have 3 channels. So we get the same bar and same scale from 0 to 255. The only difference is that we have 3 channels. So it's 255 times, actually 256 if you count from 0 to 255. So that's 256 times 256 times 256 for each 3 channels, giving us the total of 16.7 million color possibilities, right? So how do we get one pixel here that's a skin tone, right? It would be defined like this. If you remember those 3 sliders, that is how they would be defined if you were to think about this image in third dimension. And that's how we would get our color image, full color image with different channels, and this is how we would represent each of those colors for individual pixel. But if you remember, I said we were reverse engineering this image, so we're going back in history. So now we're going to strip this down back to our grayscale image, right? So we stripped away the channels, we don't need them anymore because we're going back to reverse engineer this image. We're going to focus just on this one pixel, right? So we're going to focus just on this one pixel, and let's see how this pixel would look if it had only 1 bit. We know that they had 8-bit previously. Now we're going to strip it down to 1 bit. Now 1 pixel represents a picture element, you know that, right? Well, 1 bit comes from the word binary digit. It's kind of like a shortened version of it. And in case you're not familiar with binary digits and what does all that mean, well, your computer is binary machine. In fact, all the devices you're using are all based on binary. They're binary machines essentially. So whatever they're doing, whatever they're communicating or thinking, they're doing in what is referred to as binary digits. And they go from 0 and 1. That's the combination. That's the binary system, right? And they're known as bits. So you can think of 1 bit as essentially it has 0 and 1s. You can think of it as a light switch that can be on or off. So if it's off, that's 0, that means we have black color. When it's on, we have 1, that's white color. So 1 bit can only have black and white possibilities, no other shades of gray in between, just black and white, right? Well, for our image, we saw that we need at least, if we want to show it in like a grayscale image, we need 256. That's a lot more bits. And we wanted to show our image in full color, we need that many bits per channel. So how do we get that? Well, now we're broken down our image back to 1 bit, 1 pixel. Now we're gonna go and try to rebuild the image back to its original full color state. Now you can think of this light switch as bit, and how many bits we need to create a full color continuous tone. Well, that's defined by the depth, and that's like this: when we raise that bit to the power of x presenting, well, you can think of it as depth. Technically, I don't think that's how you call it, but just for better understanding reasons, that's how I refer to it, and you'll understand what I mean in a second. So 1 bit, well, 2 to the power of 1, if you know anything about math, would give you 2. So no change there, right? So if you have 1 bit or 1 bit depth, what you get is essentially 2 potential values, just white and black. That's it. For 2 bits or 2-bit image, what you get is 4 possible values. So that will be complete black, complete white, and dark gray, light gray. For an 8 bits or bit depth of 8, now 8 bits as we used to refer to it, is 8-bit image would give you 256. That's that number that we saw earlier, 256 different shades. Now why is that number so important? Well, let's take a look. What we want is to represent a continuous tone, and for that we need bits, a lot of bits. So if you only have 1-bit image, you get 2 possible shades or luminance values. That's black and white, right? If you go for 2 bits per channel, or should I say 2 bits image, you get 4 possible shades. 4-bit image would give you 16 possible shades. And then with 8-bit, that's when you start to see a continuous tone, and for that you need 256. Let's see how that works with an actual image. Now I think you'll start to understand much better what's going on. Well, like we saw before, if we only have light switch, we only have black and white, right? If we only have 1 bit, it's very hard to represent an image as what we refer to as a photographic image. Technically that's a true black and white image, but in photographic terms it's not. It's just almost like an illustration. So 2 bits would give you a lot more to choose from. Not a lot, but visually a lot more, right? You start to kind of see what the image is all about, even though you still have only 4 shades. Well, with 4 bits, interestingly enough, you can get away with having 16 possible different shades of gray in an image. But if you take a look at her hair, for example, and that part of the image, the upper part, you can get away with that. No, you can represent that and nobody will really complain. But if you go down below her chin, you start to see those individual bands. Remember when we talked about banding? Well, that's what we want to avoid, right? That's exactly the problem we're trying to avoid. We need more bits to display continuous tone. That's why we need 8 bits or 8-bit channel mode to represent an image that has a full continuous tone. So that would give us, in an 8 bits per channel mode, we only have 1 channel, so the image is called 8-bit image, giving us 256 possible shades of gray. And that's enough for us to show relatively continuous tone, right? We look at this and we can say this is a photographic image. But unless you're trying to be artistic about your images and show them in black and white, as we refer to them, and you want a full color image, you need more than that. So let's talk about that in a minute. Now, as you remember, when I talked about a slide where you can choose how many channels you're going to have in your image, and you can also choose how many bits per channel you're going to have in your image, you can choose between 8 bits per channel, 16 bits per channel, and 32 bits per channel. And if you remember, I also said that we're going to focus only on 8 bits per channel and 16-bit, because 32-bit per channel, that's for HDR images and it's an overkill for a standard photographic image. So if you want to represent the same image we see here, but this time you want to present it in 16 bits per channel mode, you don't get twice as many colors. Remember, in an 8 bits per channel mode you have 1 channel, that's 256. In a 16 bits per channel you still have that 1 channel, but this time it's 65,536. Why is that? Well, that's because 2 to the power of 16 gives you that number. What about a full color image? Well, if you remember, we can still choose how many channels we want and how many bits per channel. So in an 8 bits per channel we can choose 3 channels, red, green and blue. So that's 8 plus 8 plus 8, giving us 24-bit image. And 16.7 million, that number, how many colors we can have? Well, that number comes from 256 remember, per channel, times 256 times 256, and it will give you that number. Well, in 16 bits per channel, when you have 3 channels, that's 48-bit image, 16 plus 16 plus 16, and that will give you incredibly amazing 281 quadrillion possible colors. And that's a mind-boggling. That's like, I think, like 15 decimal points. Just like ridiculous number. And there's no way an image would have that many, or that you would really use that many in most cases. So here's an interesting point. Photoshop, you would think that in 16 bits per channel, right, that's 2 to the power of 16 would give you that many colors, but it turns out it doesn't. This is a strange quirk inside of Photoshop, and this is now something that, well, you can think of as an Easter egg. Something that I'm about to show you, which is more for advanced users, curious people, masochists, math teachers, and so on. So this is a bunch of math now you're about to see. If you're a standard end user, you don't really care about this. But if you're just curious about it, here's what happens. When we choose 8 bits per channel, that means that we have 256 possible colors per channel, right? When we choose, because that's 2 to the power of 18, 2 to the power of 8, sorry. But if you want 16 bits per channel, you would think that that refers to as 2 to the power of 16, right? And that should give us 65,536 possible colors. But that's not what happens. What you really get is this many colors, just about half. Now why is that? Well, that's a strange quirk inside of Photoshop. If you really, it's not a problem really, but it's something that was done on purpose, but it doesn't go advertised, so many people don't know about it. When you choose 16 bits per channel, you're more closely working in what is referred to as a 15 bits per channel. Why? Well, 2 to the power of 15, which represents 15 bits per channel, would give you 32,768 possible colors. Now, we need what are referred to as midpoint. So we need one more color, and that gives us what essentially is a midpoint for simpler math when doing all those complex algorithm type calculations. And the best I was able to find is that it turns out that when Photoshop using complex calculations, especially with blend modes, using a simpler math where we have that kind of like a middle point in this big number, that what engineers in Adobe like to use more than not having that one more color to give us that midpoint. Problem is that if you have one more color, you're more than what the 15 bits per channel mode can represent. So you need the next bigger mode in order to, well, fit that 15 bits per channel plus one color, and that is 16 bits per channel because it has one more color. Now if you wanted to maintain actual 16 bits per channel in Photoshop and you still want that midpoint, then you would need the next bigger one, which is 17 bits per channel to represent that color. Like I said, a bunch of math. You don't need to worry about this, because even if you have 32,769 possible color values, that's still a lot more than having 256, right? Way more, not twice as more, but a lot more. So you don't need to worry about, even though it kind of cuts you in half of how much you really think you have, you still have more than enough. So if you're just an end user, I don't think you should ever worry about this. This is just like a Easter egg, for the curious masses, if you will. So we're visual people, we don't like math, so let's take a look at a visual representation of all these different bits. If you have an 8-bit image, that gives you 256 possible values of, or shades, or values of luminance, or tonal range, or possible colors if you have a RGB color image. Then 2 to the power of 10, that's a 10-bit image, gives you 1024, right? 12-bit image gives you 4096, 14-bit image gives you 16,384, and then 15, the one that Photoshop uses, is 32,768 plus that one color for midpoint we need for blend modes, remember? So we need 16-bit mode to represent that. But a true 16-bit modes per channel, or should I say bits per channel, actually contains 65,536. Now take a look at the chart on the right. The values are represented in tens of thousands, right? That's a lot of thousands. And check out that little white bar at the bottom. That's your 8-bit. Now check out the 16-bit, that's the purple one on the end, just how much bigger that is, right? Sometimes it's visually easier to understand how much bigger it is. When you're working in Photoshop, you're working with the blue bar, but it's still a lot bigger than the white bar. Now let me get back to this thing. When you choose 16 bits per channel, this whole conundrum with 15 bits per channel plus 1 blah blah blah, that's the only thing that happens when you're using Photoshop, right? Anywhere else when you use 16 bits per channel mode, it's an actual 16 bits per channel mode, so it gives you that 65,536 possible colors. But when you're working in Photoshop, that's the only place in your entire workflow where you need 16 bits per channel mode to just represent what is in fact a 15 bits per channel mode. Now let's take a look at the end our workflow, our raw workflow, if you will. Now this is an interesting thing because all these bits and numbers can be quite confusing, and what I thought would be a good thing to do is to give you kind of like a bird's eye view, an overview of where all these bits come from and where all these numbers really play a part. Because the interesting thing is we don't work with the same image in the same bits per channel mode in each application. They vary, and that can be additionally confusing. So let's start all the way to the left. Pre-capture. This is how we see the image. We just see a full continuous tone. Our eyes has a really good resolution, and even though it's not digital, we can refer to it as such. So we see, of course, organically, there's no bits. We're not digital, we're not robots, we're not Terminators. So to talk about bits, we first need to capture what we see, and that's done using a device like camera, right? And this only refers to a raw workflow, by the way. That's why I have that raw written under the camera icon. Most digital pro level DSLRs, digital style cameras, they shoot with either 12 bits per channel or 14 bits per channel. That's about it. Now you could find cameras that shoot lower, and I'm talking about raw files here, and you can also get more bits than that. You can get actually 16 bits per channel mode with certain cameras, but those are cameras that for most of your career you're probably not going to be seeing, and even if you do, the principle is still the same. So because they're very rare, that you don't see them a lot, 90% of cases you're going to be working with either 14-bit or 12-bit raw files, and that's what I wanted to point out. That's why I just chose two different options here. Well, before you can actually put them in Photoshop, we need to develop our raw files. We know that, right? So we need a raw conversion. I'm going to be focusing on the two raw conversion programs from Adobe because that's the one we're going to be using, both of them, both Camera Raw and Lightroom. And just so you know, if you have the same version of Lightroom and you have the same version of Camera Raw, then the processing engine and whole architecture is exactly the same. So what ends up happening is that by default you can change this, but with raw files they work in 16 bits per channel mode. Now what does that mean? Well, when you have a 14-bit file that comes from your camera and you open it up in Camera Raw or Lightroom, it doesn't magically add 2 more bits of data to it, right? It doesn't add new colors. What it tries to do is it really puts it in a container, And when you start manipulating your colors inside of an image, it uses that extra room to interpolate colors that are not there originally, but it tries to figure out what the colors might look like if you actually had 16 bits per channel. And this process is called interpolation, similar to what happens when you resize your images, when you upsample them, right? I mean, if you have a certain number of pixels inside of an image and you double the amount, you can make up new pixels from original data because that data is limited. So what Photoshop does is basically tries to figure out what the potential pixel might look like when you upsample your image. That process is called interpolation. Now, in layman terms, it could be something like if you have 2 pixels, one on the left is darker red, on the right is a lighter red, and you need to add one more pixel. What pixel would that be? Probably some shade of red in between those 2 pixels, right? That's how Photoshop, in simpler terms, that's how it tries to think. It tries to kind of intelligently guess how many new colors would look like. And what ends up happening is that we need less than 8 bits per image, per channel, to show continuous tone, to show a photographic image that we see as an interesting, full color image that doesn't have any banding or anything like that. But the only time you actually need more than that is when you're editing your file, and the type of editing that includes curves adjustments, levels adjustments, hue saturation adjustments, shadow highlights filter, things of that nature. So when you apply that to your image, not when you see it on the screen, but when you apply those type of adjustments, that's when you typically need more than 8 bits of data per channel. But if you just want to represent the image that looks great on screen, you don't need more than 8 bits to represent. You only need more than that to essentially edit your file, and not any kind of editing, but really extensive kind of editing. Because if you open up your file inside of Photoshop from Camera Raw and you just remove your few blemishes and then you print the image, you don't need 16-bit, you only need 8-bit, because you're not doing anything really that damaging to the image, right? You still have enough data to show continuous tone. Where you do need more than 8 bits, when you might choose 16 bits per channel mode, is when you want to deliver your file to Photoshop from Camera Raw or Lightroom and then work on your images, do extensive type editing inside of Photoshop. Something like I already mentioned, curves, for example. Let's say you want to retouch an image, the type of retouching that includes maybe some dodging and burning, or moving some blemishes, maybe cloning and healing, things like that. And then on top of everything, you apply curves or levels or something like that, and it's a really extensive type edit, and the image on top of that has really smooth gradients inside of an image. Well, that's the only reason why you might want to choose 16 bits per channel mode, because you want that extra interpolated data to basically not damage your file and not end up with banding or posterization. I guess another way we can think about it is that, and this is simplified terms, but when you're working with an 8-bit file, you get possible 16.7 million colors, remember? Now, a human eye, in the most optimistic estimates, in NASA-approved lab conditions, to a perfect human being under perfect lighting and all that stuff, it can see up to 10 million distinct colors in an image. So up to 10 million, not above that. That's the best estimate. And 8 bits per channel gives you 16.7. That's way more than you can differentiate. And most people can not see 10 million different colors. And of course, it also depends on an image. What kind of an image it is, how many different colors it has, and so on and so forth. So 8 bits per channel is more than enough to see a continuous tone on an image. And the same goes for print. When you print your image, yes, you can print in 16 bits, you can also print in 8-bit, but the point is that if you don't have a continuous tone, and if you don't have some kind of special case image, 99.9% of situations, when you print in 18 versus 16-bit, you won't see any difference. So if you're outputting for print, typically you want to output for 8-bit. That's how you deliver the file. And if you're preparing for web, then again, you're not editing, you're just displaying, so you need 8 bits. So the question is, okay, my camera captures in 14 or 12 bit, right? I put my image inside of Camera Raw, there I work in 16-bit. I do all my editing, all my major edits, like curve corrections, exposure, contrast, things like that, hue, saturation. I do most of those really damaging edits to a place in my workflow where I have most of the data to work with, so I at least damage my file. And then I gotta decide, when I transfer my file from Camera Raw or Lightroom to Photoshop, what am I gonna do with an image next? Am I gonna just remove a few blemishes, do some healing and cloning? What am I gonna do with an image? If I plan to do just those type of small adjustments, I know I'm gonna print or deliver the file to the web in 8-bit, so I know that I'm not gonna damage the file because I'm not doing big edits. So 8 bits, perfectly fine for working inside of Photoshop, right? But what if I have an image that has smooth gradations, like skies or something like that, inside of an image, and I know that I will be doing some type of a big edit inside of Photoshop? Well, that's the time where you definitely want to go with 16 bits per channel mode, because you want to take the advantage of that extra data that you had from your Camera Raw. You don't want to throw that away. Well, here's another thing we want to discuss. What happens if this is not a raw workflow? What happens if you only start working with an image inside of Photoshop and that image is delivered to you in already an 8-bit mode? And this is a typical situation if you're working with images you might get from stock photography. Remember, those usually are in 8 bits and they're already processed, and they're usually not raw files but JPEGs, or best case scenario TIFFs. So what happens then? And you still have an image that has some sky and you want to manipulate that. Well, another thing you can do is you can upsample it. Essentially, you can choose 16 bits per mode inside of Photoshop, even though the image itself originally came to Photoshop as an 8-bit file. This will give you some extra room. It's not the same thing as getting the image in 16-bit mode from Camera Raw, but it's the next best thing. And I'll show you some examples where that is beneficial, and when you might want to choose that for editing purposes, not for displaying, just for editing. So what this whole chart was about is to give you an understanding that all these bits, we know now how much we need. We know now that where in our workflow those bits are coming from, and this is all just theory for now. We're gonna show all of this in actual images, in true photographic images in different genres, different examples, so you'll get a visual understanding of what's going on. But just so you know, when we talk about certain numbers like 15-bit, 14-bit, 16-bit, 256, 65,000, blah blah blah, that you know where do they come from, and where in your typical raw workflow would you have many bits. Okay, and now we're gonna discuss in some later videos on actual real-world examples when would you use what. So you'll see that you need 16-bit not always, and it's not a good idea always to use it, and a lot of times it's actually counterproductive, as you'll see. So the only time when you might use it is when you know you will be editing your file inside of Photoshop. That's it. Only place when you have an actual benefit from it. And we'll see how that works in some of the future videos. Well, I think this concludes this video. It's been an interesting ride, and I'm sure you saw here a bunch of information. Most of it you probably didn't pick up in your first viewing, so you might check out this video for the second time. But I think that once you see the rest of the videos with this one, you're gonna start connecting the dots. The more time I expose you to the same numbers, to the same data, to the same ideas about workflows, the more you'll catch on and you'll be better at understanding. Now I understand where I need to use 8-bit, 16-bit. There's not a mystery behind anymore. Okay, this is where I get the problems in my image, this is where I not get the problems, and it will become more natural to you. You will know on image by image basis when would you choose 16 or 8-bit, or you will know that based on your common type workflow which one works best for you. And you're not going to be not, there's a lot of mysticism and controversy behind bit depth, so people tend to listen to people who are not experts and who have really no understanding what they're talking about. So they just use more bits because somebody told them, hey, that's more data. That means that the attitude, mine is bigger than yours. It's just a fail-safe, an insurance. And other people go about, well, I don't print histograms, so you can show me that more bits actually mean better image. And the truth is somewhere in the middle, as it always is. It's dependent highly on the context, and this is a theory behind what's going on with this bit depth, right? But the context itself is the key to getting the end result as you want it. And that's something we're going to cover in the future videos with actual images. So we're going to show different context for different images, and then when we choose which bit depth to give us the best results. And hopefully you'll, by the end, bit by bit, you'll have a pretty good grasp of understanding what's going on with your images. And then when we go into color management and gamut of your images by using color profiles and so on and so forth, then you'll also run into these numbers and bit depth. So if we don't talk about that right now and you have a good understanding, then later when it becomes more complex, it will just create more confusion. That's why I'm going kind of like bit by bit. No pun intended. So see you in the next one.